These two properties are so important because they preserve the structure of the vector space that we give them a special name. We call them linear transformations. So what we'll do now is a process of abstraction, which is similar to the trick that we pulled for inner product. Remember what we did for that. We noted the properties of the dot product in Rn that we liked so much, and we listed those properties as a proposition. But then after that, we took those properties and used them to make a definition, or stated them as axioms, if you like, of an inner product. And so here we'll do a similar thing with these maps. We'll take these properties which these maps satisfy, namely the properties that they preserve addition and scalar multiplication, and we'll use those properties as axioms or as properties for a definition of a new kind of map, which we call a linear transformation. So here's the definition. Let V and W be two arbitrary vector spaces. A function from V to W is called a linear transformation if these two properties are satisfied. I'll call them property A, if F preserves vector space sums, that is, if f of V plus W is f of V plus f of W, and B, if F preserves scalar multiplication, that is, if f of R times V is R times f of V. Just a note on terminology. For my videos, I quickly grew tired of writing the word transformation over and over again. So I shifted, and I will shift, to the also commonly accepted term, which is linear map. So I'll call linear transformations linear maps because I often do, and it's easier for me to write down, but it means exactly the same thing as linear transformation. Let's look at another example of a map which is a linear transformation, and then just to be clear, we'll give an example of a function which is not a linear transformation. And so here's our example number 1. We'll give 3 or 4 examples, so the count begins here. Example number 1. Consider the map L, we'll call it L, from R4 to R2, defined as follows. L takes a vector x, y, z, w, and the image of such a vector is the vector x, z. So we claim that L is a linear transformation. There are 2 properties we must verify. Property A, that L preserves vector space sums, and property B, that it preserves scalar multiples. So let's check. First, our verification that L preserves vector sums. So here's how this goes. What I'll do is essentially two operations in different orders. So up here, I'm first going to add the 2 vectors, and then I'll apply the definition of the linear transformation. So from here to here is just vector addition. From here to here is application of the definition of L. L picks out, there they are, the first and the, whoops, that's a typo. Should be the first and the third, 1 second. There we go. L picks out the first and the third components. Now let's do the same operations, but in a different order. So now, first we'll apply L, and then after that we'll add the result. So if we do, applying L to the first vector gives me this thing, applying L to the second vector gives me this thing, and then we add them together to get this thing in the end. And we see, of course, that this vector and this vector are precisely the same vector, and therefore L of V1 plus V2 is equal to L of V1 plus L of V2. Let's see if property B of a linear transformation is satisfied. This is the property that L must preserve scalar multiples. So again, a similar pattern. We want to verify that if we do these operations in 2 different orders, we get the same thing. So here, first we're multiplying by the scalar R and then applying the definition of L. So here can you see scalar multiplication from here to here, application of L from here to here. And here on the bottom, we're doing those things in the opposite order. Here, first we're applying the definition of L, and then we're scalar multiplying by R. And of course we see that we get the same thing here and here. These expressions are equal, and so we can conclude that L satisfies scalar multiplication as well. So properties A and B of the definition of linear transformation are satisfied. We can conclude that this map L is a linear map. For our next example, let's consider the function L from R3 to R2 defined as follows. L takes a vector xyz and maps it to the vector x squared y 0. So this is certainly a map from R3 to R2. And let's see if it's a linear map. Again, we have to verify properties A and properties B, so we'll begin with property A, where we will attempt to verify that L satisfies or preserves the vector sum. So to see if L is a linear transformation, we'll begin with property A to see if we can verify that L preserves vector sum. So we do the same thing. We first add two vectors and then apply L. So here's vector addition from here to here, and here's application of L from here to here, and we get the following. So notice that the whole first coordinate x1 plus x2 is squared, and that's the result. So here's the other calculation. First we'll add, first we will apply the vectors L, the map L to these two vectors, which is what we're doing here. And then we'll add the two vectors, which is what we're doing here. And so we get this vector right here. But here's the problem. This vector is not equal to this vector. These are not equal. And so we can conclude that this map L, although it is a map from R3 to R3, this map L is not a linear map. That is, it is not a linear transformation because it fails to preserve direct sums. If this isn't abundantly clear, let me make sure it is. So the problem is, if I can zoom in, that here the first coordinate is x1 plus x2 quantity squared. But down here, the first coordinate is x1 squared plus x2 squared. Well, you should remember that those are not the same thing, right? The first one, x1 plus x2 squared, is x1 squared plus 2x1 x2 plus x2 squared. And this one down here, of course, is missing that middle term. So this map L fails to preserve vector addition. It is not a linear transformation. What about property B, scalar multiplication? Can we check to see if L preserves scalar multiplication? Well, we could, I should say, but there's really no reason to at this point, because we already know that L is not a linear map, because it fails at least one of the two conditions. It fails A. So whether or not it fails B is irrelevant at this point.